This is part 2 of lesson 1.12b for core chemistry second semester. And we were just talking about how the gymnast would probably beat the sumo wrestler in a 100-meter dash because higher mass molecules travel more slowly than lower mass molecules. So slow moving molecules interact more. Okay, so because they're moving slower, they're going to bump into each other more. They're going to have more of an interaction versus the fast ones, which are just going crazy and bumping over here and over there, and they have nothing to do with each other. Molecular shapes. Now remember, we're talking about what determines whether a substance will be a liquid at certain conditions. We care about the shape. Compact molecular shapes, such as tetrahedrons or linear shapes, so really nice and tight together, will help molecules pack closer together, thereby allowing for stronger intermolecular forces to hold them together. All right, so we can look at some of this stuff. We can look at methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. Now, hopefully you've noticed something about these. All these have anes, and we're going to talk about what that means later. And they have different prefixes, which actually mean 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which you can see by the number of carbons. So it's how many carbons. So which one of these is the biggest? The decane is the biggest, and we can see that it's liquid. The smallest one is the methane, so it's zooming all over the place, and at room temperature, it is a gas. The sparse spaces between liquid molecules allow them to flow. Remember, there's empty space in between the molecules of the gases, but there is a little bit of space between our liquid molecules, and that lets them flow. Honey is a viscous liquid, viscous meaning thick, that flows better when it's warm because it becomes less viscous and therefore thinner. Imagine a cup of liquid as a pickup truck with marbles filling the bed. The marbles are close together, but they can still roll around one another. If you put down the back gate, the marbles will roll out. Liquid molecules act in much the same way. The molecular behavior allows liquids to flow. Even as liquid molecules flow past one another, they exert intermolecular forces that resist flow, so it slows them down. This resistance is called viscosity, so the resistance to flowing or how thick it is, and it's proportional to the strength of the intermolecular forces. Examples of viscous liquids include syrup, honey, and motor oil. You can change the viscosity of a liquid by heating it. The added energy breaks the bonds of intermolecular forces. Okay, so they're not stuck so close together. They have more energy, they're zipping around more, they're interacting with each other less, they're a thinner liquid. Hydrogen bonds are one example. You can see this change when you warm honey or syrup. Similarly, high heat from a car's engine makes the motor oil thinner or less viscous. So, more heat, more motion, less viscosity. The sparse spaces between liquid molecules make the molecules only slightly compressible. Because of the sparse spaces between molecules, liquids are only slightly compressible and much less compressible than gases. So gases, we can really squeeze that balloon tight. Liquids, we can squeeze a little, but not a lot. Liquids transmit pressure. This is huge. This is the property that is used in hydraulic braking systems like those in a car. Have you ever thought about it? How you, little you, can stop a car going 75 miles an hour just by pressing gently with your foot? I mean, really? Think about it. It's because of the brake fluid. It's because of hydraulics. It's because the liquid is taking the pressure that you're applying and it's going through the lines, it's changing the size of the lines that the pressure is going through, and it exerts a huge force to stop the wheels. Charles' law says that gases expand a lot when heated. By contrast, the intermolecular forces between liquid molecules tend to hold them together and keep liquids from expanding very much when heated. Yeah, they do still spread out when they heated, but they don't go crazy and fill up the whole room like gases do. Car brakes stop tires by applying the properties that liquids are slightly compressible. Intermolecular forces give liquids surface tension. So here you can see it's like a film on the surface of this water where the bug is. It kind of almost looks like plastic, right? But no, it's water. The force of intermolecular attraction within the water buoys particles on the surface or holds them up, thereby creating surface tension. Have you ever noticed a water strider walking across the surface of water? Maybe you have floated a paperclip on the surface of a glass of water. What holds the water strider and the paperclip up? Surface tension. Surface tension holds them up. It is a property of liquids, and in water it is especially high. Here's how surface tension works. Any particle deep within the liquid has an equal number of molecules around it, right? It's surrounded on all sides. And the intermolecular forces in the molecules equally attract the particle. However, at the surface, the number of molecules surrounding the particle is not equal, right? Because on the surface, it's not just water touching it, it's the air. And that imbalance draws the liquid molecules closer together. They want to be by their friends, they want to be by each other, so they get really, really close together. And that's what makes a film. Whereas down 8 feet, when you go diving into the pool, the water molecules there have equal water molecules everywhere. So they're happy. They're just kind of like, yep, I'm by my buddies, I'm okay. On the top, they're like, no, no, don't make me go by the air. Come here, give me a tighter hug. Yeah, just like that. That's how they say it. And that's what makes surface tension. High energy liquid molecules escape into vapor phase. Liquid molecules escape into the gas phase where they exert vapor pressure. High energy liquid molecules escape into vapor phase. If you pour a liquid like water into an empty container and seal it, you will find that some of the water molecules will enter the gas phase above the liquid. The gas molecules will actually exert a pressure called vapor pressure. So vapor pressure, the pressure exerted by a gas on a liquid in a closed system. So kind of like how we have atmospheric pressure. If you have a jar with water in it, the air, the gas that's trapped in the jar above the water is pushing on the water. That's called vapor pressure. This vapor pressure happens even when the liquid is not boiling. Each molecule in a liquid has kinetic energy. At any given time, some of those molecules have more kinetic energy than others. Those few liquid molecules with the highest kinetic energy can break free the intermolecular forces and move into the gas phase. So this is evaporation. As more molecules go into the gas phase, they exert a pressure back down on the surface of the liquid. Some of those vapor molecules slow down. And when they slow down, what happens? They condense back into liquid because they have less kinetic energy. Because the container is sealed, a steady state or equilibrium occurs, where the rate of vaporization, so the rate of some of the water molecules on top getting free of the water and becoming gaseous, equals the rate of condensation. So the same rate, some of them slow down, they hit the top of the container, they turn back into liquid water. And a steady vapor pressure is achieved. At higher temperatures, more liquid molecules have sufficient kinetic energy to go into gas phase, thus increasing the vapor pressure. So in other words, higher temperature, faster they're moving, the more are going to go into the gaseous phase. Vapor pressure and boiling are closely related. So heating a liquid increases kinetic energy in the molecules and increases the number of molecules that escape into the vapor phase. Vapor pressure increases with temperature until at some point the liquid boils. You can increase the total pressure above the liquid. So if this was sealed, we'd be talking about the pressure of this gas right in here. You can increase the total pressure above a liquid artificially by putting a lid on the pot. In this case, the trapped water vapor exerts more pressure back on the liquid. Therefore, the temperature of the liquid must go higher for the molecules to escape. Okay, so if you have a tight seal on here, you're forcing these gas molecules down, and so the water, it needs more energy to escape. As a result, the liquid will boil at a higher temperature. This is the principle behind a pressure cooker. Okay, so we're forcing it down and we need more and more heat energy for it to go, no, no, I'm going to escape. As a result, the liquid will boil at a higher temperature. This is the principle behind a pressure cooker. By contrast, if you reduce the total pressure above a liquid, so you take it off, then the liquid does not need to reach such a high temperature to boil. Okay, now if you're saying, well, I always put the cover on so it boils faster, yeah, that helps keep the heat in, so that's why. We're talking like a super tight sealed cover, okay? This is also different at different altitudes. If you live way up in the mountains of Colorado, you have less air around you, less air pressure, so there's less pressure pushing on the molecules, so they boil at a lower temperature. Intermolecular forces explain many liquid properties. Liquids have volume but no definite shape. The strength of intermolecular forces compared to kinetic energy determines the phase of a substance. For liquids, intermolecular forces is greater than kinetic energy. Intermolecular forces hold liquid molecules close together, but the molecules can slide past one another and move about. The sparse spaces, so there's little spaces between the liquid molecules, unlike gas, right? Gas has lots of space between them. Allows the molecules to flow and compress only slightly. Intermolecular forces bind liquid molecules at the surface to form a film and support particles, surface tension. Liquid molecules with high kinetic energy, so lots of energy, can escape into the vapor phase, and if it's sealed, they exert vapor pressure, so they put pressure back on the liquid. When vapor pressure equals the total pressure above it, the liquid boils. Liquids' properties are strong intermolecular forces. They can be viscous, so thick or thin. They are slightly compressible because they have little spaces between them, and liquids flow. As always, if you have questions, let me know.